So in the last class we have discussed about methods of proof, like one particular statement or theorem is there, how we can able to prove. For that we have seen several methods. Before discussing these methods, we have proved by you arguing based upon the definition or based upon the facts. We have argued, and then we have concluded convincingly that particular statement. Like we have seen the number of odd vertices in the odd degree vertices in the graph will be always even. Such kind of things, or sum of the degrees of all the vertices is 2 into number of edges in the graph. Like that, some of the theorems we have proved, and we have proved those theorems by using some observations or some definitions or some facts. Okay, but there exist several other methods which are more applicable in practical sense. Like whenever we wanted to prove some what you call, suppose if you write a program, this is an important discussion, man. Try to understand, even though you feel little awkward at the beginning, try to accustom to it. Why? Because if you understand this particular one, you will be the supreme in your team. Okay, after completion of graduation and all, you will work somewhere in the industry, most probably. So if you have this kind of fundamental knowledge on basics, then you will be leading the team. Okay, try to understand the point here is like we are having a program. Let us say addition of two numbers. I think everyone could able to write. Yes or no? Everyone could able to write addition of two numbers. Now the question is, now you tell, what is the guarantee that whatever the program you have written is correct? This is the question. Understand my what you call my point? Yeah. Suppose you have written a program to calculate factorial of a given number. Then how you could able to say that whatever the program you have written, that is correct? In general, yeah, tell.
We will check the algorithm.
You will check the algorithm. Okay, algorithm is also like pseudocode only, right? Like whatever the program you have written, based upon the algorithm you might have written, so that algorithm will contain some steps, same steps only you will be saying. But again the question will arise, like what is the guarantee that that algorithm is correct?
We will give some inputs and take the outputs of that.
Okay, okay, let us consider addition of two numbers only you have written, and you are claiming that your program is correct. So you have mentioned some inputs, like 5 and 10 if you give 15 you are getting, 20 and 30 if you give 50 you are getting, 50 and 100 if you give 150 you are getting. Like this, you have shown plenty of examples, and you have claimed that that is correct. Now is it sufficient?
No, sir.
What can be the other thing, or why it is not sufficient, you try to tell.
Because there could be an example where algorithm would fail, and we haven't proved that that example doesn't exist.
Okay, okay, for this you tell what's the counter case, what can be the counter case for addition of two numbers. Suppose you have taken three variables, integer a, b, c, and you have read the two values like a and b, and c is equal to a plus b, printf or print c value. That's it. Okay, fine. This is the program. This is absolutely will give the sum of the two numbers. But if a value is 10 lakhs, b value is some 5 lakhs, then will it be able to add both the numbers and give the result? It depends on the range of the variables that you have taken. You have declared the two variables as a integer, so it will work within the range of integers. But if you go beyond the range, then it will not give correct answer. It will give answer definitely, but it will not give correct answer. So there is no guarantee, isn't it? Understand my point?
Yes, sir.
Yeah. Suppose you have written factorial of a given number. Factorial of a given number, 5 means 120 will be 80, 4 means 24, 3 means 6, 2 means 2, 1 means 1, 0 means 1. If I give the input as -1, then it should not allow, right? Or it should give justifiable answer. Suppose same you consider in other way, like 10 factorial, how much will be the value? Will it fit within the range of integer? 12 factorial, will it fit? You can maximum you might have checked up to 7 factorial, I think so. 6 factorial, 7 factorial, that's it. You felt that program is working, everything is fine. But if you go beyond the 8, 9, 10, then automatically the integer range will gone. So your program is not at all correct. So what can be how we could able to claim that whatever the program you have written is correct? Understand my point now?
Yes, sir.
Yes, sir.
Yeah. So even you consider just printing patterns, like you will be having 1 1 2 1 2 3, like so such kind of patterns you might have seen in first year or somewhere, like, right? Yes or no? Have you seen or not? Please respond, ma. If you don't see them, please tell. Like this, ma. 1 1 2 1 2 3, like this.
Yes, sir.
Yeah, you will be using 2 loops. One is to represent rows, one is to represent columns. Then you could work out. But for this also, you should give a guarantee that always your program will work. Okay, not only as I have mentioned in basic programs like addition and factorial, I have mentioned, like if you increase the size, then it will go. That is not only that particular possibility, there exist several other possibilities as well. Okay, for such cases, whether it could able to give the correct answer all the in all the time, wherever it is allowing the input, if it gives correct answer, then we can say our program is correct or our algorithm is correct. So how we can prove that program is correct? That is the question. In order to answer such kind of questions, we are having these methods of proof. Okay, let us see one by one. I think we have discussed irrespective of what you call independent of this kind of intuition, we have discussed due to what you call, I thought of giving this also in test 1, that's why I have discussed. Afterwards I didn't satisfied with the one class itself, that's why I left this. Yeah, come to this discussion, like p1 p2, p implies q, we can be written as p1 and p2 and p3 so on pn. So p can be what? Conjunction of p can be conjunction of several statements, like p1 p2 p3, that can be substituted, like p can be substituted as like this. This can be represented in other way, like p1 p2 p3 so on pn. If all these are true, then we can conclude that q is also true. And here in this p is called as, or p1 p2 p3 so on, we call it as hypothesis or premises. Okay, this these words are important, try to remember it. Okay, next this is a conclusion. Q is called conclusion. And whenever p implies q represent universally correct method of reasoning. When p implies q represents universally correct method is whenever the result is tautology. That is, if P implies Q is tautology, then we can say it is universally correct method. That is universally acceptable method. Now the question is, try to understand this. This we will use at the end of the class maybe. This you need several times afterwards as well. Okay. Try to understand P implies Q. What is the truth table final column result? P implies Q result. Or you tell what is the truth table of P implies Q?
It will only be false when P is true and Q is false. Remaining all the time, it will result in true.
Yeah. So here we'll be having true only whenever P is true and Q is false. Then only it is false. In remaining all cases, it is true. Yeah. So this is the truth table of P implies Q, which we have seen already. Now I am saying the result is tautology. Then only it is universally correct method. Okay. Whenever this P implies Q is when this particular P implies Q becomes tautology, this is the question. When this becomes tautology, if you don't have this F, then only it will become tautology. Yes or no? Try to understand the simple point. If you don't have this F in this particular column, then it will become tautology. Correct?
Yes, sir.
Yeah. Now the point is, when we do, how we can avoid this case is, if you don't have here F, then we can avoid. Yes or no?
Yes, sir.
Yes.
Yeah. In other words, even if you have F, we should not have T here. You consider this is the counter case. Even if you have F in Q, we should not have T here, so that we can have resultant as true. Now the point I will say in a straight way. This is an intuition. I try to understand the point. In order to avoid or in order to get only true in this particular column, whenever P is true, whenever P is true, definitely this Q is also true.
True.
Then we can claim that P implies Q is tautology. I'm repeating once again. If P is true, then then Q is also true, then we can say P implies Q is universally correct. Is it okay? I'm repeating once again. If P is true, Q is true. If you say this this particular one is holds, okay, this statement is holds, then can we say P implies Q is universally acceptable, universally correct?
Yes, sir.
Yes. Why? Because this is the only case where we are getting false, but that case we are guaranteeing that that case will not arise. So definitely, irrespective of other truth values, whether Q is false or Q is true, or P is false or P is true, this combination T and F combination will not arise at all. So we will be getting P implies Q as tautology. Okay. Based upon this only, everything we will work out afterwards. Okay. This you keep in mind. Now, I think you have got what is the meaning of this particular one. Result. If the result is a tautology, then implication P implies Q is universally correct method of reasoning, and it is called rule of inference. Next, this is implication, like P implies Q is true and Q implies R is also true. Then we can say P implies R is true. How we can prove this? By using truth table. We could able to prove, and if you observe the true what you call the truth table contains tautology. All the values has true, so it is tautology. So based upon this fact that if the result is a tautology, then implication represents universally a correct method. So is this clear so far? Yes.
Yes, sir.
Yeah. Now you consider other important one, that is modus ponens. Next, here we are having P as true and P implies Q is also true. When this is possible, when P is true, P implies Q is also true, we are saying, then Q must be true. Yes or no? If P is true and P implies Q is true, then Q must be true. Okay, that's why the conclusion is Q. So this is modus ponens, and this can be observed in what you call truth table method as well. When we obtain a truth table, we will be getting tautology for this. So it
This
is
is
also, yeah. Any
this is this is like mathematical induction, sir. P could be the base case, Q could be the, I don't know, repetitive case. When base case is true, and
hmm, hmm.
if
Ve-
if
very good, very good observation. That is absolutely correct. Absolutely correct. We'll see in today itself. We will see that mathematical induction also. How we can link this to that, we'll see. Yeah, of course. This only the intuition for it, for mathematical induction. This is the basis. In order to prove that P implies Q always true, what we have to claim is this particular one. We will assume that it is true, and we will prove that Q is also true. That is what the basis. Yes or no?
yes, sir.
Yeah, we'll see. Yeah, quickly I'll go through this. These all we have seen in previous class itself, and we stuck that. Yeah, we stopped here. Proof by contradiction. Proof by contradiction. Here we are saying P implies Q is true, and negation Q. Then what is the conclusion? Negation P. How we can prove this is, we have seen one example, like square root of 2 is irrational. This is what we have to prove. Then square root of 2 is a rational number. This is the statement that we are assuming as P, and Q is there exist m by n values. Okay, m by n. Okay, further it cannot be divided. That you please keep in mind. M by n, in m by n representation we will be using, like 5 if we have 5 if we have, can we say n by 2, m by n representation is 10 by 2 or 15 by 3? Yes or no? Are these two true or not?
Yes, sir.
Yes, sir.
But but intuitively it is correct. But m by n represented not only m by n, whatever the m by n we have, further we could not able to, we could not able to reduce it. Like 5 can be written as 5 by 1. Yes or no?
Yes, sir.
Yeah, here also we could reduce it to 5 by 1. We could reduce it to 5 by 1. So it is not the m by n representation which is used to claim that it is a rational number. 5 by 1 if we give, then that is correct. Understand?
Yes, sir.
Yeah. Now based upon this, we will try to move, like square root of 2 is a rational number, then we can find m by n, m and n. Okay, this is what P implies Q. And now what we have to prove is there does not exist m by n corresponding to square root of 2. For that, this is the proof. We have seen m by n whole square. If you do, then we will be getting 2, isn't it? M by n is square root of 2. What we will assume? Proof by contradiction, in the sense we will assume one statement. Try to understand this. 1 minute you try to understand. Then that example you will understand. Yeah, we will assume that one particular thing is true, and we will continue by assuming that as the true, and we will continue further, and we will come to know that that is not at all true. Then we can claim that whatever the first statement which we have assumed as true, that is false. Understand? Or in other words, I can say, like we will assume that p is true, and we will continue like this. and some after some observations we will come to know that this is not p implies q does not hold. P implies q does not hold. Then we will say that whatever the assumption we have made, that is false. That is negation p is true. Negation p is true. Understand? Yes, negation p is true in the sense p is false only, right? Whatever the assumption we have made, that is not true. So p is false, so negation p is true. Yes or no?
Yes, sir.
Yeah. So if you understand basic intuition here, then we'll see the example. You will be clear with the concept. Yeah. Basic assumption here is we can represent square root of 2 as m by n. So m by n is equal to square root of 2. If you square these both these sides, we will be getting m by n whole square is equal to 2, and m square is equal to 2 into n square. Till this point, it is clear to you. Now here m square is equal to 2 into n square, in the sense m square is definitely definitely
Even.
even number. If m square is even, definitely m is also even, right?
Yes,
You
sir.
consider m value as 3, then m square will be 9, so it is also odd. Any odd number square will be odd only. So even number square only the even, so m is even definitely. And one more thing, if m is even, it will be divisible by 2. Yes or no?
Yes, sir.
Yeah. So if it is divisible by 2 means m square means will be getting like 2 into some m1. M is nothing but 2 into m1 whole square. Can I write like this or not? Because m is even, so it is some multiple of 2. 2 into 1 or 2 into 2 or 2 into 3, like that, some multiple of 2. So to m square I can written as 2 into m1 whole square. Is it clear? This is simple thing.
Yes, sir.
Yeah. Now what is this one? 2 1 2, if you put here, what we will be getting here? 2 into m1 square. Yes or no? 2 into m1 square. This is nothing but n square. This component is nothing but n square. Yes or no? M square is equal to 2 into n square. That is nothing but 2 into m1 square. Is it clear?
Yes, sir.
Yeah. Now n square is even or odd?
Even.
Even. So if n square is even, what about n?
Even.
Yeah, n is also even. So this is the thing. N is also even. Now what we can understand from this is, starting from this, m by n is square root of 2. This is what we have assumed as true. Then m is even, n is even. This is what we have claimed. Now if m is even, let us say 14, and n is also even, we are saying, so it can be 2, or it can be 4, or it can be 8, or it can be 6, whatever it may be. So let us assume it as a 12. Now is this m by n representation correct? 14 by 12 or 14 by 2, 14 by 4?
No, sir.
No. So we can conclude that there is no such m by n representation. Yes or no?
Yes, sir.
Yeah, this is contradiction. This is contradiction to what? Whatever the assumption we have made. That's why it is called as proof by contradiction. We assumed that one statement is true, and if you analyze by continuing that assumption, we will arrive with the contradiction, and we can say that whatever the assumption we have made, that is false. So here you say, therefore m by n is not the most reduced form. We can pull a 2 out of both m by n. Okay, both m and n, we can pull 2, right? Like 2 into 7, 2 into 6 we can write. So 2 we can pull from m and n. So this is not the reduced form, definitely. So this is a contradiction. So whatever the assumption we have made, that is whatever the assumption we have made, that is
False.
false. Yeah. So if p is false, negation p is true, right? What is negation p? P is this. What is negation p?
Root 2 is irrational.
Yeah, root 2 is irrational. That's it. Like this, we can prove statement by using proof by contradiction. Yeah, any doubt?
No, sir.
Okay. Let us say quickly this one mathematical induction, as you have pointed. What is the normal what you call method for mathematical induction? First, we will this mathematical induction. There exists one thing like one constant called n naught. This you remember. After this n naught only, we will try to prove that one statement is true. Okay, let us say one statement. The statement is f of n. F of n is true for all n where n is greater than or equal to n naught. Starting from n naught, whatever the values we are having, for those values only f of n is true. That is what the statement. Statement or we can say the theorem that we are trying to prove is f of n is true for all n greater than or equal to n naught. For remaining values only we will be proving. That you keep in mind. That is very important one, which usually people will be missing. In I think I don't know exactly how you have learnt mathematical induction in intermediate or somewhere. You start by taking n value as 1. For that you will claim that it is true. Afterwards you will assume that for n is equal to k it is true, and we will prove that n is equal to k plus 1 also it is true. Yes or no?
Yes.
Yeah. But why we have to consider n is equal to 1? That is not standard. N is equal to 1 is not standard. That you keep in mind. We can take any n naught. It can be that f of n can be true starting from 5, starting from 10, or starting from n naught. So for that particular n naught, we will first check f of n naught is true or not. Okay, whatever the cases you have learnt earlier, like n is equal to 1, in that particular case n naught is equal to 1. Okay, that is not wrong, but I am saying that is not complete. N is equal to 1 case we will not check for all the times. Okay, for some cases we will consider that n is equal to 1. Understand the difference?
Yes, sir.
Yeah. Now, what is the first step? First, we will prove that f of n naught is. We will prove that f of n naught is true. Next, second step is for k, we will assume that f of k is true. And third step is actual induction step. What we will do for f of k plus 1, we will prove it as
True.
true. That's it. Then we can claim f of n is true for all n greater than or equal to n naught. This is what the claim. Now, here also you can observe that implication which we have seen earlier, like a true and false case. If we avoid, then it will become tautology definitely. So this case, how we can avoid is whenever p holds, definitely q must be true. Then we can avoid this case. Then it will become a tautology. This is what the intuition. So based upon that only, this mathematical induction has defined. Yeah. Now let us see one by one. As you know this method, I don't want to spend much time on this. Like this is the statement. For this, what is n naught? N naught is 1. So for 1 we will say it is true, and we'll assume that for k it is true. Then for k plus 1 we have to write. So LHS will be 1 plus 2 plus 3 so on k plus 1, which is nothing but we know up to this k into k plus 1 by 2 plus k plus 1. If you what you call simplify, we will be getting like k plus 1 into k plus 1 plus 1 by 2. It is of the form n into n plus 1 by 2. So we can claim that it is also true for f of k plus 1. Okay, like this we could prove our theorem. Next, this we will see in detail. Like you consider a1, a2, a3, so on an be any sets. Now we have to show that union of like a1, a2, a3, so on an negation. Okay, complement is equivalent to intersection of a. like you consider what is the De Morgan law. What is De Morgan law? A union B whole complement is nothing but A union B whole complement is equal to
A complement intersection B complement.
yeah, A complement intersection B complement. So it is similar to that, but we are having more than, it is an extension to this. So how we can prove is, for one particular similarly similar to earlier one, for base case, like if we have only one, A1 complement is equivalent to, here intersection we cannot apply on one particular set, so A1 complement. So first case is true, base case is true, A1 complement is equivalent to A1 complement, that's it. Next, what is the induction step? We will assume that P of k is true. That is, for P of k, A1 union A2 union A3 union so on AK bar. Okay, A1, let us consider A1 union A2 union so on AK whole complement, okay, or AK whole bar is equivalent to A1 bar. You please tell. A1 bar intersection A2 bar intersection A3 bar so on AK bar. This is what our assumption. This is P of k is true. Now we have to prove that P of k plus 1 is true. How we can, what is the LHS of P of k is nothing but A1 union A2 union A3 union so on AK plus 1 whole bar. This is whole bar, okay, whole bar. Now it can be written as union is associative, like A union B union C can be written as, we have discussed this, A union B union C can be parenthesized in any way, right? Either A union B union C we can write, or A union B union C, both are same, yes or no?
Yes, sir.
Yeah, so it is called associative property. So as we are having here how many unions, k plus 1 sets union, so we can write first k sets as one set, one unit, and k plus 1 as another unit. Like this we can write. Now you apply De Morgan's law. What is the formula of De Morgan's? A union B whole complement. Here we are having one, this entire thing is A, let us assume this is A and this is B. Okay, A union B whole complement. What we can write? A complement, that is this entire thing, A complement, then B complement. Yes or no? Simple application of this, simple substitution of this formula. Clear?
Yes, sir.
Yeah. Next, again, what can be written? This can be written as up to AK minus 1 we can consider as one unit, this as A and this as B. Then this can be written as, again, by substituting in this formula we will be getting A1 A2 A3 so on AK minus 1 complement intersection AK complement. Yes or no?
Yes, sir.
Yeah, like that if you continue further we will be getting like A1 intersection A2 intersection A3 intersection so on AK plus 1. Okay, this I think this notation is known to you. Intersection I is equal to 1 to k plus 1 in the sense A1 bar intersection A2 bar intersection A3 bar intersection AK plus 1 bar. Is the notation clear to you? Intersection.
Yes, sir.
Yeah, okay. So like this we can prove that P of k plus 1 is true. P of k plus 1 is true in the sense, whenever P of k is true, then P of k plus 1 is true. So if you consider the truth table, we will be getting the tautology. As we have assumed earlier, like we have seen rule of inference. Whenever the implication results to tautology, then we can say that is rule of inference, and that is universally correct. That is the principle of mathematical induction. Clear? I think now you have got what is the taste of this P implies Q, why we are stressing on that. Yes.
Yes, sir.
Yeah. This is another example. This you can go through. Just I will give you the glimpse of it. Like the statement is, consider the factorial. 1 factorial is 1, n factorial is n into n minus 1 factorial. This we know, and this can be observed that n factorial is greater than or equal to 2 power n minus 1. This is what the fact. Okay, this statement we have to prove. For that we will use mathematical induction. Base case we are assuming it as 1. So p of 1 is true. Why? Because 2 power 0 is 1. So greater than or equal to 1. So it is true. Next, p of k is true. We are assuming that p of k is true. So k factorial can be written as greater than or equal to 2 power k minus 1. This is what we can assume. Next, for k plus 1 we have to prove what is k plus 1 factorial. K into k plus 1 factorial, and k factorial we know that it is 2 power greater than or equal to 2 power k minus 1. So we can substitute here, then it will become k plus 1 into 2 power k minus 1, and this k plus 1, k is greater than or equal to 1 as we have assumed. N is greater than or equal to 1, so k is also greater than or equal to 1. K plus 1 will be 1 plus 1 at least. Value of k is at least 1, so 1 plus 1 it will be 2, so it will be greater than or equal to 2 into 2 power k minus 1. We can write this one as 2 power k. And one small clarity I wanted to give here, we are writing it as equal to in the sense it is equivalent to this one, not it is equivalent to k plus 1 factorial. That you keep in mind. Whatever the thing we have written in the previous step, with respect to that we are writing here, not with respect to this. Okay, so k plus 1 factorial can be written as greater than or equal to 2 power k. So for k plus f of k plus 1 is also true, we can say it is tautology, and we can claim the statement n factorial is greater than or equal to 2 power n minus 1. Clear? Any doubt?
Clear, sir.
Yeah. And this is an important discussion that I will discuss in the next class. I don't want to rush in this. Yeah. Okay, if you have any doubt, you can ask.